This meeting is being recorded.
Okay, well, we're at 1 minute after the hour. Why don't we go ahead and get started? Welcome to the Air Sea Fluxes from Space webinar series. Today we have David McCann from the UK National Oceanography Centre, who's going to talk about airborne remote sensing of ocean surface processes. And I'll let you take it away, David.
Fabulous. Is my screen still sharing, by the way? I
You're
can't
not
actually.
sharing, so.
No, I didn't think so. Okay, well, at least I know how to do this now. Okay, is that up on your end? Because I
That's
can't see
it.
you anymore.
That's the perfect mode, yes.
Fabulous. Okay. Well, good afternoon, everybody. I'm David McCann from the National Oceanography Centre. I'm a senior research scientist over here, and my specialisation is in the remote sensing of ocean surface properties with microwave radars specifically. So I'm going to talk about a couple of projects today. One was funded by the European Space Agency, and another project that we started a year ago funded by the Advanced Research and Invention Agency, ARIA, which is quite an exciting project, but all in the theme of measuring the dynamics of the ocean surface from the air. So for the first half of the talk, I'm going to concentrate on a long track interferometric synthetic aperture radar. So this is a microwave radar technology that uses two core processes of measurement. One is interferometry and the other is scatterometry. So interferometry is the process of measuring the phase shift between two signals, transmitted and received signal, between two antennas that are separated by a physical baseline. And this whole unit with the baseline is moving a long track, so flying in the same direction as the platform. And with this, we measure the phase velocity, the movement of scatterers on the ocean surface in the radar line of sight. And then the second process is scatterometry, which is simply the measurement of the returned power of that microwave radar signal as it scatters off these same scatterers on the sea surface. And this correlates very strongly with wind speed. So in order to get our geophysical properties that we care about, so in this case, we care about ocean surface currents and wind, we have to take our measurands, which are our normalized radar cross-section from our scatterometry and our Doppler phase, our interferograms from the interferometry. We mix these with a geophysical model function, and then out the end, we get our geophysical properties. Now, these technologies are about 40 years old now. So Airborne SAR ATI was first described by the seminal work of Goldstein and Zebker back in 1987, where they flew an 18-meter long L-band array, really quite a large array, on this NASA Convair Coronado, where they made the first line of sight observations of ocean surface motion. I think this was in the Bay Area, but this was their data from their short paper. So very simple line of sight observations, but the first line in the sand, as it were. And then in the 90s, there are a number of experiments, but quite an interesting one was the high-res experiment, which flew a similar L-band array. I think maybe the same one, although I haven't been able to find out whether it was the same or just very similar, but an 18-meter array again on NASA DC-8. But this time they flew these line of sight measurements in two orthogonal directions, so a northerly flight and an east-west flight, to produce the two orthogonal components to make an ocean surface motion vector, which you can see on the right-hand side here. So these were the first 2D current vectors created with these technologies. They also produced the first comparisons with other remote sensing data. So there were some comparisons with HF radar surface motion measurements as well. Then in 2005, the WaveMill satellite mission concept was put to ESA, and this the idea behind this was to combine these two orthogonal looks into one instrument, so that you can measure or you can observe a total surface current vector from a single pass. And to do this, there are 4 channels. So you can see the instrument design on the left there. So 4 channels with 2 squinted along track interferometric looks. And these are squinted 45 degrees to the flight direction and 90 degrees from each other to get that orthogonality. And then in 2011, this was turned into a real instrument, the WaveMill proof of concept instrument, and it was flown on a C-47B Dakota over the Liverpool Bay area in the UK. So Liverpool Bay in the Irish Sea back then was home to the Coastal Observatory, where a bunch of near permanent observing systems were in operation, including an HF radar looking over the sea there, and some in situ buoys. So this demonstrator campaign demonstrated the first 2D surface current vectors mapped from a single pass. It was also the first independent validation of really quite an important geophysical model function of Alexei Mush, his 2012 GMF. So this is quite an important GMF for space-borne ATI work. So this was the first independent validation of that, and really quite a successful campaign. But one of the big outputs of this was that in order to create these total surface current vectors, you end up with ambiguities, and the ambiguities are related to the wind direction. Now, in order to solve for these ambiguities, it was found that a third independent look to solve for the wind direction was really quite essential. So this led to the OSCAR instrument, the Ocean Surface Current Airborne Radar Demonstrator, and this is where I joined in with all of this fun in 2022. So this is an ESA-funded demonstrator for the SeaStar mission concept. SeaStar was an ESA Earth Explorer 11 candidate to measure global, coastal, total surface current vectors and ocean surface vector winds from a satellite. And the demonstrator instrument was built in the same configuration, albeit much smaller. So this is a KU band 3-look SAR system with a combined interferometric and scatterometric modes. So we have 5 channels. You can see the antenna array on its boom and the top image there. We have 2 ATI channels squinted at 45 degrees to the flight direction, much like the WaveMill demonstrator. But with this third independent look, this broadside mid-channel, it produces very high resolution SAR imagery and also a phenomenal amount of raw data. I think it's about 500 megabytes per second. And this was designed, owned and operated by Meta Sensing, where it is permanently mated with this Piper Navajo airframe. So one of the things you might have noticed to start with is that the baselines, the arrays of these systems and the aircraft have all been slowly shrinking over this last 40 years. So I'd like you to keep that in mind for the second part of the talk. But first, we're going to concentrate on some data and campaigns that we ran with OSCAR on the Piper Navajo. So as part of the SeaStar candidature for Earth Explorer 11, we ran an experimental campaign called SeaStar X, and this was run firstly over the Irwa Sea in May 2022. We also ran a second campaign over the Mediterranean Sea in 2023, although I won't be talking about that today. So for the Iroquois Sea campaign, we flew 4 scientific flights of Oscar over the ocean there. So this is west of Brest in France and around the island of Ushant or Ouessant in French. And this is an area where we have very strong, it's a macrotidal environment, really strong tidal currents, but also we targeted areas of homogeneity and also some open ocean flights that were designed to compare the scatterometric properties of the instrument and the winds that it can generate with ASCAT, but that was performed by a different team. So we also had a load of in situ measurements. We had an ADCP on a mooring. We were supposed to have an air-sea flux buoy, which would have been great for this talk, but unfortunately it filled with water and also smashed itself on the hull of the ship as it was being retrieved, which is just a standard story when it comes to in situ campaigns. So unfortunately have to get used to that, but we don't have the in situ wind component, unfortunately. But we also have a bunch of other remote sensing data, including an HF radar array that looks over this area, an X-band radar, as well as various numerical modeling and numerical weather prediction products. So the first flights that we'll talk about flew over this dynamic tidal race around the island of Ushant. And this is quite a famous area. The La Jument Lighthouse is in sight of these tracks. Quite a famous, picturesque lighthouse out in the Atlantic. This is where the X-band radar was mounted to the top of this tower. It provided a very valuable test of the system in response to really intense gradients and our ability to pick up very large signals. In many respects, it's the low-hanging fruit when it comes to these kind of data because the signals are so great, but it was a good test of the system. We also had some overland flights, which we can use for interferometric relative calibration, because with the land not moving, you can test that your interferograms show you zero Doppler movement. Then we also had some flights in over the open ocean. So just a little further out to sea, there are some quite homogeneous areas of the ocean, quite deep. And we flew 8 tracks crossing over a moored ADCP, which in the diagram on the left, you can see the ADCP in that red spot there. And this was the so-called star pattern acquisition method. So we have 8 tracks that have flown in 45-degree intervals. And the idea here is to give each of the 3 looks of Oscar the same opportunity to see all azimuths relative to the wind. So the whole pattern only takes about an hour and a bit to fly. And through our in situ data and the models that we have, we can prove that we have temporal and spatial homogeneity. So what we can use this data set for is to really test the response of the system and the dynamics that it measures relative to wind direction and relative to the geophysical conditions. It's really quite a unique experiment. You can't do this from space, of course, because your orbit is not relative to the wind direction at all, and you can't change it relative to the wind direction. So we really want to dig into these data a lot more. We've got some ongoing work and some papers that we're in preparation at the moment. But it's a fantastic data set, and I will plug this until the cows come home. It's a really good data set to work with. But anyway, to turn these data into currents and winds, we use a simultaneous retrieval method that is based around the minimization of a cost function. So our input data are the normalized radar cross-section, the sigma naught images from the 4 mid and aft channels. And then we have the interferograms from the squinted channels fore and aft. These interferograms are turned into radial surface velocities. So not line of sight velocities, but velocities along the sea surface. And these are all passed into this cost function here. So it's split up into two sections. We have a scatterometric part and an interferometric part. As you can see, they're broadly the same. You have you're looking for differences between your measurements and some kind of model. So those are highlighted in red. So for the scatterometers, Ku mod, so this is the modulation of Ku band backscattered return. So for this, we use NSCAT 4DS, which is a tried and tested geophysical model function for predicting the modulation of these frequencies of microwaves with respect to the wind. And then for the interferometry, this is the tricky part. So for the Doppler velocity, the so-called wind wave artifact surface velocity, we need to model the predicted motion of the scatterers for a given geophysical condition and take this away from our measured observed surface motion in order to get a current. Now, there are precious few of these GMFs available in the white literature, certainly. We have Alexei Mush's GMF. There's also one by Yuri Yurovsky from 2019. But apart from that, there's very little. So this is an open area of research. It's really quite vital to get this right because the predicted Ku Doppler here, the WASV, is a big number in the meters per second, and the measurement is also big. So if you are looking for a small current, let's say in the open ocean, taking a big number away from a big number can be very problematic for your errors. So this again is something that we're looking into quite actively at the moment, and we've got some more work coming forward, hopefully. This is going to be an issue for Harmony, especially going forwards. So yeah, we'd like to spend a lot more time on this. I'm not going to talk about the ins and outs of the WASV today because it's a bit dry, but it's an important topic nonetheless. So the outputs, the pretty pictures from these data are here. So this is one of our overland tracks from the 17th of May. In the Irwa Sea campaign, we have the currents from Oscar on the left and the winds on the right. So this is equivalent to the U10 wind above the sea surface. And these, I think it's important to remember that these are derived simultaneously from the same data set. So we can't have one without the other. I said that the SAR data was to 8-meter resolution, but at 8 meters, we pick out the orbital motion of waves. So we average down to a coarser resolution. This is to 200 meters, but we could go as far as 100 meters. This was mainly a choice for computational efficiency primarily, but you can see these fantastic gradients. This is during the ebb flow around the island, so up to 3 meters per second. We have a return eddy down south and the southern part of the jet. The swath width here is 5 kilometers because we're flying at about 10,000 feet, three odd kilometers altitude. So that's a consequence of the flight altitude and the incidence angles that we look at. And the wind speeds look very reasonable as well. And they we'll get onto some comparisons in a moment, but really quite nice data out of this instrument. So this was reported in our 2024 paper in Ocean Science. So we have our first comparisons between the various data sets that we have over this area. So we have, apart from Oscar, we have a 2DH numerical model, Mars 2D, which is developed by LOPS in France. We have the X-band derived surface currents from La Jumente Lighthouse. Unfortunately, not covering much of our swath, but that's a consequence of the range of the X-band. And then also we had some really beautiful Novasar 1 imagery from about an hour's difference, I think, from our acquisition, with our current vectors overlaid on it. I think what's really nice about this as a simple visual cross comparison is it really highlights the differences in these different methods, the position of the jets and the shear zone of this current between a numerical model, which has obviously very idealized conditions, smooth bathymetry, the X-band, which is seeing different properties of the ocean surface than we're looking at, and then of course the Novasar 1 synthetic aperture radar image, which picks up very different properties than we pick up because of its difference in incidence angle. But otherwise, I think a really nice look at the different data types. For the winds, we don't have anything apart from numerical weather prediction data, but this is from Météo France Airborne, which is the operational wind forecasting system of Météo France. So we'd like to believe that it's probably the best wind model for the region, being French. It's also much higher resolution than products like Aero 5 and ECMWF. So being quite close to the coast, some of the orographic effects we would like to think are better represented. But we have a really good visual match, at least here in this image, and even some of the north-south gradients in the winds that were predicted. Now, when it comes to the validation, we use the homogeneous open ocean area. So not quite as interesting to look at, unfortunately, but really important for our validation for the Seastar concept. So on the top here, we have the simultaneously derived current velocities and wind speeds and the directions as well for Oscar. And these have been collated, all of the different tracks of the star pattern, into one map. And then on the bottom, the two models, just for visual comparison here. So Mars 2D, lovely and boring, 60 centimeters per second flowing north, and Arum, which is showing a sort of a northeasterly wind of about 6 meters per second. What's quite interesting is that we're seeing already some spatial variability in the winds with Oscar. We see this especially in some of the Mediterranean data that we unfortunately can't talk about today, but I think it's quite it's interesting to see the differences between observations and models, especially when it comes to the differences in resolution with spatial variability. The temporal variability comes in here a little bit as well, perhaps. It is over an hour to complete the whole pattern for Oscar, so we could expect some changes in wind speed. But anyway, very pleased with the visual comparison. But the validation that was used for the UCM, we assumed temporal and spatial homogeneity across the pattern. So we took the mean retrieved parameter for each track, and then we produced an RMSE comparing to the ADCP, which was in the middle of that pattern, and we met our design requirements for the system, which was 10 centimeters per second on velocity and half a meter per second for wind speed, and also quite close with the direction as well. Of course, no in situ wind comparison, which is unfortunate. So for the winds, we had to use an interpolated Arum product. We're working on a publication for this at the moment, and we're adding in all of the other data that we had from the campaign, including the HF radar data, other wind products as well, to look at doing a triple co-location as well as a simple RMSE. But I think we can prove that the system works quite nicely. It's just very difficult to get the GMFs right, which is a story for another day. But I'd be happy to talk about that afterwards if anyone is interested. So the second thing I'd like to talk about is an exciting new project that we have just started about a year ago. So this is Aerostat, which is the aerial experimental remote sensing of ocean salinity, heat, advection, and thermohaline shift. which is quite a mouthful. So Aerostats is funded by ARIA, which is a new funding agency in the UK. For those not familiar with it, this is sort of the UK's answer to DARPA. So it funds high-risk, high-reward research. And we at NOC are leading this project with project partners in radar metrics in Spain, Noveltis in France, and Pixelytics in the UK. So the whole MO of the program, so we're funded as part of a program called Forecasting Tipping Points, which is looking to forecast or observe indicators of tipping in the North Atlantic climate system, specifically around the Greenland ice sheet and the North Atlantic subpolar gyre region. So this is a region that is really on a knife edge in terms of its health, its heartbeat presently. And it's a really vital region for the overturning engine that really drives not just northern hemisphere climate, but global climate as well. So up here we have the cold fresh water from the Arctic flowing down the east coast of Greenland. This is mixing with the warm salty water of the North Atlantic in the subpolar gyre, and this forms our deep water that drives the overturning circulation. And this deep water formation, this convection, is something that has got people quite concerned. Specifically, its ability to convect and then drive the subpolar gyre, and the future health of this system has really dire impacts for our climate in the UK, especially, which is why ARIA is so interested in funding it, but also climate in general. So one alarming thing, I guess, is that our models of this system are showing tipping points effectively. So this is a high resolution model. This is some work that Alice Marzocchi, who's part of our consortium at NOC on this project, produced. So this model is showing the winter mixed layer depth averaged over the Labrador Sea region from 1990 all the way up to the 2090s. And what it's predicting is the intermittent deep convection as we observe in the current era, leading to a gradual reduction in mixed layer depth, but then an abrupt cessation of mixing around 2040, a so-called tipping point. Then after that, we have a new stable state with very weak mixing, a new state with a lack of dynamics. So this is the kind of tipping point that ARIA are interested in looking at. And I think what's important to raise is that not all models are showing this, but frustratingly, it's the highest resolution models that tend to show this behavior. And we just do not have high resolution data to really validate these models. A lot of climate models are not exactly based in reality, let's say. And I say that as an observationalist, so maybe a little bit biased. But we really don't have observations to back this up either way, which is where we like to come in. So this region on the east coast of Greenland is absolutely fantastic for dynamics. So this is a Sentinel-3 sea surface temperature image from 2023. And you can see these wonderful sharp contrasts and gradients of temperature, which also correlate with salinity in this case. This is cold, fresh water from the Atlantic, flowing in a very coastally constrained current that is basically following the shelf break. Very steep bathymetry here, all the way down the east coast of Greenland. We see some wonderful sub-mesoscale dynamics in these eddies and fronts at around the kilometer scale. But this is really not a representative image at all from the region. So you can see some cloud in this Sentinel image, but the cloud cover is borderline 90% averaged each month throughout the year in this region. It's incredibly cloudy, and it's a persistent problem, not just for sea surface temperature optical product, but also ocean color. Ocean color products are really excellent ways to make inferences of the vertical exchanges from looking at the different pigments of the different zooplankton and phytoplankton that we can see on the sea surface. But we really don't have much data, or it's certainly enough data from this region. From space, that's not just related to the cloud cover, the temporal frequency of these images is not enough to really resolve the temporal variability of the system, and the spatial variability is really difficult to observe when you can't see the sea surface as well. We have a similar story with the winds. So the winds around this region are, well, they borderline terrifying. So this is an ERA 5 analysis that Jeremy Grist, as part of our project, has done, looking at the average hourly maximum wind all the way from the 1990s to the present day. So each of these subplots is by month, and you can see that the average hourly maximums are way up in the 20-30 meters per second for much of the winter. And for reference, 20 to 30 meters per second is beyond a gale, severe gales to storms. And this quick scat image on the top right shows us one of these tip jet events where these phenomenal winds blow off the southern tip of Greenland at Cape Farewell. They can exceed 50 meters per second. So hurricane force winds as a wind event. Now, what's problematic with these data is that they miss the variability. So QuickScat is seeing winds of 40-50 meters per second, but averaged over very, very wide areas, and not looking at much in time, let's say. So we can expect that the real maximums in wind speed could be even higher. And because air-sea interactions and fluxes are non-linear, we could be really missing out on some very important drivers of heat between the atmosphere and the ocean in this area, and also fluxes of heat the other way, which are then being passed to the models that are doing the predictions for climate. So these parameterizations, we worry, are really missing some of the extremes in variability that in this region are not extreme events, but rather just the extremes of everyday physics. So we need much better wind data. And then there's a similar story with the salinity. So in situ salinity is very difficult to get in this region from in situ campaigns, especially because of the sea ice that is present for much of the year. We have some, I think these are from maybe from floats. I can't remember what this data is from. Hopefully Adrienne's on the call and can pick up a question if there's any questions on this later. But we have quite sparse in situ measurements, but these sparse in situ measurements do show very strong variability in sea surface salinity in this coastal region here by the east coast of Greenland. The satellite-based sea surface salinity is problematic in its own respect because it has trouble with the sea ice content of the ocean, and also the land contamination from. So these are radiometers with quite wide beam widths. So the closest that we can get is about 100 kilometers ish, maybe, from the coast, which misses the very thin coastal current that we showed earlier. So we're missing the ability to measure the temporal and spatial variability and salinity of this system as well. So to recap on the background for this, these systems form a vital part of the Atlantic overturning via the supply of cold, fresh water to drive deep water formation and convection in the Labrador Sea. It's an area of extreme strong gradients and intense spatiotemporal variability, but it's also really poorly observed. So we have very few in situ observations, and they're restricted to summertime campaigns that are free of sea ice or to limited moorings like the OSNAP array, which of course doesn't look at the surface, but rather the subsurface. Or some like the Erminger Sea OOI mooring, which is unfortunately going to be decommissioned soon, are very limited in their spatial extent. And satellite EO can't solve our problem because it's either too untimely to resolve temporal variability, has limits to its spatial resolution or scope to observe small-scale dynamics and variability, or it just simply can't see the sea surface for most of the time. So this is where aerostats come in. So this was proposed as a 5-year project. As I said, we're a year in now. We were funded for the first 2 years. We are now putting in our bid for the final 3 years of the project to start next year for our campaign. But we propose to make better observations of the exchanges of freshwater and heat between the ocean, atmosphere, and cryosphere in this really vital region for climate. But we're going to focus on the fine temporal and spatial scales that we believe really drive variability. So we have 3 key objectives. The first is to demonstrate affordable, long-term, low-carbon EO monitoring with new airborne platforms. Secondly, to develop a new compact, high-resolution imager for total ocean surface currents and ocean surface vector winds. This is Seastar Air. This is our follow-on from our Seastar work. And also, finally, to demonstrate year-round observations of ocean color, sea surface temperature, and sea surface salinity in the region, but most importantly in winter and cloudy conditions. Now, if you remember from the early slides, our airborne work in the community over the last 40 years has been slowly moving to smaller and smaller aircraft and smaller technologies. So what we're proposing here is the next step from a general aviation solution, and to bridge the gap between sort of standard aviation airborne EO and satellite EO to make something much more affordable long term. So to do this, we have been focusing on innovative autonomous airborne solutions. So for the last 12 months, I ran a review of everything that is available, and we had a bunch of front runners. We looked at uncrewed aerial systems or drones. We looked at airships, and we also looked at high altitude pseudo satellites or stratospheric drones, fixed wing drones. And the result of this was the selection of the Boreal Lab drone, the French drone that you can see in the center there, and also in the left-hand image with some of our project team standing beside the fuselage. So this is a fixed wing, 4-meter wingspan drone. It weighs 25 kilograms, which is the EASA limit for sort of simple light drones. This is sort of an industry standard weight that everybody builds to these days. It's powered by a traditional ICE power plant. It's a 2-stroke engine. But most importantly, it meets all of our campaign objectives. So it has a payload, pardon me. It has a maximum payload weight of 5 kilograms, with which it can fly for 8 hours and for 800 kilometers of range. It has a good cruise speed, but most importantly, it's very cheap. Has a GRP construction for its fuselage. It's made to be mass produced. Boreal are now tooling up their production, so it's becoming much more scalable. They're also a company that have their roots in oceanography, so they're really quite engaged with what we do. This is a system that's been used for monitoring seagrass in the Sargasso Sea, but also for maritime monitoring around French maritime interests as well. So in this drone, we are going to be flying 3 different EO packages that are all being either developed or put together as part of the program. Each is as revolutionary as the other for its size and its ability to be mounted in such a small drone. So the first one is Sea Star Air, which is a brand new ATI SAR imager for currents and winds that's been developed by Radarmetrics in Spain. This is a 5 kilogram SAR system that its electronics there. You can see some of the scale of this. So the antenna arrays are about 7 centimeters. The electronics about 20 by 20 centimeters. And there's an impression of one of the ideas of how to mount it in the drone there in the right-hand image. This is a C-band SAR system, and it's designed to be not only compact and light, but also very low power. This will be a revolutionary system, we hope, in the future, and we can think of 1,000,001 uses for it outside of Greenland. So we're really quite excited about this. We have no data to show you, unfortunately. It's very much in its nascent phase at the moment, but we're hoping to fly this early next year as part of a test flight campaign in Europe aboard a Boreal drone. Then the second EO package is for sea surface salinity. So this is being led by Adrien Martin at Novelties in France. And this is using or repurposing L-band soil moisture radiometers for ocean observations. So one of the examples here from Terrorad Tech is on the right. It's a compact L-band radiometer that's used for example, for mowing golf courses. They're very low weight and size and low cost when it comes to marine equipment. Through some modeling that Adrian's done, we believe it's sensitive enough to resolve these strong salinity gradients, even in cold water. But it's looking to be paired with a second radiometer, a C-band radiometer for sea surface temperature and wind speed sensitivity. As I said, satellite salinity observations can only get to within circa 100 kilometers from the coast with low temporal and spatial resolution. So this will really provide an unparalleled look at the ocean surface density environment in this region. Also be capable of producing SST at night, and most importantly, can be integrated with the drone and will be flown as its own system. And then the third package, last but not least, is Ocean Color. So Ocean Color is really quite important for looking at the health of these systems and for deriving something about the vertical. There's a NASA PACE image on the top right there with a wonderful big bit of cloud in the middle. So we have these beautiful sub-mesoscale dynamics obscured by cloud. So we need to be able to make measurements below the cloud. So what Sam Lavender at Pixelytics in the UK is doing is finding either hyper or multispectral optics that will be flown on a drone below cloud, which is a low light environment at all times of the year. So both in winter when we have very little light and in the summer, to make observations of ocean color. So we are planning to fly these systems year round, but especially in winter, which is there's almost no ocean color measurements in winter. So as I said, we've picked our drone and we have our sensor packages. So with these, we are going to be making these 3 different observations in all seasons, especially in winter, to make observations of the fluxes of heat, salinity, and primary production. And eventually, this will all filter into an early warning system for climate tipping points. Now, I haven't spent any time on the early warning system part. This is a very active area of debate, let's say, in the program. We are providing observations for this, but our project is also spanning work areas in the program to also look at the modeling of these early warning signals. But we've just started to plan our campaign, so we are planning to fly in 2028, and we're planning to fly in all seasons of 2028 through probably 4 seasonal campaigns. And hopefully you can see my mouse move around while I show you through this. This is an example of our campaign planning map. So this is a map of some eddy kinetic energy that is derived from SWOT level 4 geostrophic current data. So SWOT, the Surface Water and Ocean Topography mission, for those that are unaware, is a NASA CNES mission, a scanning swathe altimeter, absolutely revolutionary for this work. It's a beautiful instrument, and we can get some really interesting things out of it, including things like a geostrophic eddy kinetic energy. So this is for the 30th of March, 2024. And as you on this plot we have the color, which is the eddy kinetic energy, which is a proxy for dynamic variability. The vectors are the geostrophic current L4 product. Then we also have a gray line, which is the shelf break at 1,000 meters. If you remember, the currents and all of this cross-shore variability and gradients are constrained to the shelf break. The yellow dots are the O-snap array moorings in the North Atlantic, and then the red dots are our potential bases of operations. Now the red range rings are from my exercise. I performed an exercise to model the time on station that would be available from this drone, flown from different stations. So this is these concentric rings are in hours. So what we're now doing is focusing in on the areas we would like to look at. So what we're starting to look at is areas where we have a confluence of the shelf break for that cross-shore variability, high dynamic variability from the eddy kinetic energy, some in situ data that's already present in terms of the buoys, and an ability to be on station for at least 3 hours, because from the temporal variability analyses of the winds that we've been doing in the program, in the project, we see that we need an update rate for the winds of at least 3 hours to really get the extreme variability that's important for the fluxes. So these are the kind of areas we'll be looking to fly at, and we are hopefully flying in 2028. This is very early days yet, and we have a phenomenal amount of planning to do, but we're really quite excited about it. And yeah, that's it for me. I've kind of talked directly at a screen of my own slides without seeing anybody, which is very strange. So I'm going to finish now for any questions, and then I'm going to exit this screen so I can see you all again. Anyway, thank you for listening.
Thank you so much, David. Questions? And maybe while people are thinking of questions, I'll just ask about the aerostats program we've just been talking about. You're talking about this in campaign mode, but you're also talking about monitoring. So I'm wondering how you're really envisioning that playing out.
That's a fantastic question, Sarah. So yes, very early days in terms of our ideas around this, but we are currently planning to bid for some extra money to turn this into an operational system. What's really important in Greenland is that something is left, the capacity is left in Greenland. They really run by a mantra there of not for us without us, or not about us without us. So what we're looking at is spooling up a Greenlandic local monitoring campaign, with the dream of this being a permanent 365-day-a-year presence. Of course, how that is paid for very long term is anybody's guess. But yes, this is what we're planning. This has to be a system that is cheap enough and usable enough that anybody can pick it up. So what we're really interested in is creating a system or suite of systems that can be farmed out to this kind of work and run operationally. But yeah, it's a very difficult question to answer. It's kind of how long is a piece of string, but we've started to think about it. Yeah, certainly.
Thanks. I see that Roger Samuelson has his hand up. Roger, go ahead.
Yeah, thanks, David, for a very interesting talk there. I wanted to ask about a technical detail that you had not said too much about, but the one question is the choice to optimize use the cost function that contains both the scatterometer winds and the Doppler surface current at the same time. I'm just curious why you chose that, because it seems like there's a much longer history for the scatterometer winds and things are pretty well defined there, whereas the cost function of the GMF for the currents must be a little bit more speculative. Do you
Absolutely.
find that, yeah, so do you find that you improve the winds by including that current, the cost function element?
It's more the other way around. So the much better defined GMF for the winds, it really helps us narrow down our total surface current vector measurement. Now, the reason that we have to do it, well, the reason that we want to do it both at the same time, is that this was designed for a system that would operate without any ancillary data. So you could do this with external wind information, in which case you just feed the wind information into the Doppler GMF, and then your current spits out the other end. But this system was designed so that everything is done with a single measurement. What we found was that the currents really do improve using a simultaneous approach rather than a sequential, as we would call it, approach of getting the winds first and then defining the currents. But of course, this is all done with Oscar data. So effectively, getting the winds out of Oscar using NSCAT first, let's say, or another system. We worked with some colleagues in Spain and China who have their own system for getting winds out of the NRCS data, and we could do that and then get the currents out with those. But we find they really improve the currents, them being solved at the same time. The winds, they pretty much, yeah, you're completely right. It's a much better defined problem, and it's much easier to solve because it's a more mature area of research, scatterometry. But yeah, absolutely. When it comes to the Doppler side of things, it's very early still, and we still need to do a lot more work. I hope that answers your question. Sorry, I realized that I just started to wander off.
Yeah, no, okay, that's good. That's interesting. I guess maybe I could ask just a little bit further about the GMF for the currents. Are you trying to derive that from the physics? It seems like the ones that you mentioned, I think, at least go in that way as far as they can, rather than, say, for the Doppler scat instrument that Ernesto Rodriguez and others have developed, that's been a much more empirical GMF, I think, that they've used. I'm just curious which way you're going with that.
So we the GMFs that we have available, like Mush's GMF, is a globally averaged thing made with Sentinel-1 data, and then Yurovsky's is a much more empirical GMF from, I think it was in the Black Sea, a radar on top of an offshore offshore station there. They have their own pros and cons, but both of them are just empirical models. There's no physics-based GMF available yet. We we know that some folks are working on this. What we have started to do is try to make our own empirical GMF, which I didn't talk about today because it was really quite dry. But the data that we have, both from the Iroise Sea and from the Med Sea, we've started to look at first making our own empirical GMF, but then also a different way of making a data-only GMF or estimate of this WAS, this wave Doppler. And it's promising, but it's still early days. So using Oscar data only, we're quite interested in seeing how you can use these instruments just on their own, especially for missions like Harmony, who are going to need to really nail this if they're going to make good currents, especially over the open ocean where the currents are very small and the wave Doppler is very big. But yeah, there's a lot to be done, absolutely. And we'd like to do some more work on it in the future.
Okay, great. Thank you.
Thanks. Other questions? Can I ask a technical question then? You made a point that you needed 3 looks to, I think with Oscar, to deal with ambiguity. I know that the Doppler scat instrument manages with 2 looks, and I'm wondering what the difference is.
That's a really good question, and I don't know how well I could answer that. I feel like Adrienne would have a better handle on that than I do. We what was found with the wave mill ambiguities is sort of that classical 4 ambiguities separated by 90 degrees, and picking which one within 180 degrees of each other, that's where that 3rd look was really required from. Oh, I can see Adrienne's popped up. Would you like to answer that? Because I feel like you could do a much better job, Adrienne.
Yeah, I'm not sure. Yeah, I can answer, but yeah, the 3rd look was very critical to get sensitivity to the wind direction for some specific wind conditions. So, for example, when the wind is blowing in the direction of one of the antenna, we have low sensitivity to the wind direction. So, as we assume that the wave Doppler is directly linked to the wind direction, we have a big error. So yeah, for the ambiguity, it doesn't really help us. So in theory, it should help us, but in practice, we have seen with Oscar that it was not sufficient because the noise level was strong. But yeah, this 3rd. So yeah, I don't know how Doppler scat deal with this. I guess because yeah, the squint is not constant along the source. So in some cases, the retrieval will be degraded, but it will not be the case for the full source. So perhaps it's a way to solve this. So.
Yeah, Alex Montier is on, so maybe he'll comment.
Yeah, I was just gonna say, hey guys, I'm sorry, David, I missed your talk. I came in late, but I came in at the right time, I guess, for this question. So if you don't know me, I wrote the wind processor for Doppler scat and many other things on Doppler scat. The main way we handle it is we actually have more than 2 looks. We have 2 looks when we're flying along in a single swath, but then we overlay multiple swaths offset by a little bit. So as we overlay those swaths, we actually get multiple looks, more than 2 for each point on the ocean surface.
Interesting. Oh, thank you, Alex.
Yeah. We also do some fancy things in the wind processing to remove ambiguities, but that's a whole other story.
Yeah.
Great. Well, we are at the end of an hour, so people may have other questions and they can email David directly. Thanks very much for the great presentation, and thanks everyone for participating.
And thanks a lot. Good to see you again, and
Yeah.
see you again next time.